All right, class, in this section, we're going to take a look at radical graphs. Now we're going to consider what the graph of a square root graph looks like. I always look at that square root symbol and it kind of helps me frame the graph in my mind. I just memorize this is the parent function. It starts at 0, 0, and then it kind of takes off sideways like that. If you want a couple t-table points, this should hit at 1, 1 because the square root of the input of 1 is 1. And then if you want to get up to a height of 2, well, the square root of 4 is where you'd have to go. So the square root of 4 is 2. So the input is 4, the x, and then the y would be 2. And then if you want your next point, you got to go all out. That was a terrible line, but you go all the way out over here to 9 to get your next point because the square root of 9 is 3. So that's the parent function. You would just do an input-output table, but I've memorized it's just this kind of sideways curve that's going through those square root results of 1, 2, 3. Now, what we're going to do is move that function using our function transformations. We learned that anything on the inside of our function that's working with the x causes a shift to the left or right opposite of the sign. The idea here is that this is going to cause a shift to the right from this parent graph. So all we're going to do is take this -3 information and know that this initial point needs to move to the right 3 spaces. So we're going to go 1, 2, 3 spaces to the right. And that's how functions transform. The inside here moves to the right. And then on the outside, it says +2. Well, this causes an up or down shift, same as the sign. So this is same as sign. This is a +2, so we're going to go up 2. And this on the inside was left to right, opposite of the sign. And so what we're going to do is take this function and shift it to the right 3, and then we're going to go up 1, 2 spaces. So my original first origin dot moves to the right 3, up 2, and my new graph will start right there and have that same shape, same behavior. And what you can actually do is go to Desmos.com and get a graphing calculator. Just want to show you how this works on Desmos. What we can do is say on the outside 2 plus, you can see it shifted up 2. And we can say on the inside here, the x -3. We can see that it sure enough shifted to the right 3, where that coordinate is at 3, 2, with the same form as the original parent graph. So if you type in square root with x, you get that parent graph, and you can see that shifted right and up. What you can do here is actually play with Desmos and say -h, and on the outside plus a k value, and it'll do, what you can do is add these sliders, and as we move k to a negative value, you see it go down. As you make it positive, it goes up, and as we have a positive h value here, we can see that it moved to the right, and as we have negative h values, you see it move to the left. So any number that's negative on the inside is a result of it actually being a minus a negative, which is why we're moving to the left. And so if you just say plus, it might be easier to think that way. So as we have negatives as we have negative h values, you see the graph is shifting right. And as we have positive values inside there, it'll move to the left. And now let's talk about the cube root of x graph. The cube root of x graph kind of looks like the square root graph, but then shifted to the left also. So what we've got here is a graph that hits the origin kind of at the twist moment. And so you see that it moves to the right and the left forever. So what we'll do is we'll add a cube root. We got to use the keypad down here. You add functions. You can see the cube root is way down the list here. Where you actually get the option to do any root. So we click that N root, and then we're going to put cube root and then x. And what you see is this is the cube root of x graph. And we can do the same thing we showed a minute ago. If you say plus h on the inside and then plus k on the outside, if we have a positive value for k, you see the graph shifting up and down, up for positive, down for negative. And then if the h on the inside is a plus, it moves left or right opposite sign. So if it's positive, it moves left. If it's negative, it moves to the right. Now, the h value itself is opposite of that. I'm just trying to show you in the inside, this is a plus. If I have got a minus going on, it's going to move right. If it's negative on the inside, it moves right. If it's positive on the inside, it moves to the left. So you'll have transformations of cube root graphs also. You can always just type your equation in here on Desmos and it will show you what the graph is supposed to look like. So now let's simplify roots of powers. What I would like you to do is to see this as a division of powers, where this root goes on the bottom. So what I like to show is that this is really a base to a fraction exponent, x over y, where this index is your y, root of some base to the x power. So it always works out that the y, the index, goes on the bottom of the fraction. So in this case, this is going to be x to the second over 2, where this index is this 2 right here. And so what happens is these divide to be 1. So this is x, the result is x to the first power. Now, whenever we have an even root where it produces an odd power like this one, you have to use absolute value bars on your answer. The issue is that although we have simplified correctly, if you put in a negative value like -1 in here, it would have got squared. And then that would have turned into +1. And then you would have square rooted it, and that would have kicked out 1. Or if I didn't use 1, maybe say -2. So you put -2 in there for x, that would have turned into a +4. And then you square root that, and that turns back into a 2 again. Well, in order for our answer to work down here, we're just saying, oh, well, it's just the number you started with. Well, it's actually the number you started with, but a positive version of that. So that's why we use the absolute value bar anytime you have an even root that kicks out an odd power. Now, we don't have to worry about that on the next one because we have an odd root and an odd power on the inside. Odd is the key here. So the idea is you take x to the third and divide it by 3. This 3 is on top, the index is on the bottom, and that does matter. So this turns out to be x to the first power again as my answer. I just don't put the absolute value bars this time where I did last time. Now here, because we have a negative inside there getting squared, what will happen is we have -x to the second over 2, and that reduces to be -x to the first power, but you have to put absolute value bars on the result. And that actually makes it to be a positive x. So you could say the answer is just x, but a positive one. So the negative here doesn't matter in the end because you're taking the absolute value of it. Over here, this is going to be x with a negative sign on it to the 3 over 3 with this negative sign hanging out for the ride in front. And so what's going to happen is these powers reduce. So this is going to be negative times -x to the 1. And that just turns out to be a positive x. Continuing here, we've got a higher power situation. So this is going to be x to the 10 over 2. Remember, this 10 goes up high, as I showed over here with our formula. And then this 2 goes as the denominator. And then we reduce, and that's going to give us x to the 5. As soon as we see an odd result, an odd power, we have to put absolute value bars on the result. So my answer is the absolute value of x to the 5th. So anytime it's an even root, and after reducing, you get an odd power, you have to put that there. Now, if it was like the square root of x to the 6th, and the result turns out to be, let's do 8. So the result turns out to be x to the 2nd. We don't need the absolute value bars because this is even, and the even will take care of making things positive. So if this was to the 12th, and my answer was x to the 6th, I don't need the absolute value bars. You only need the absolute value bar when the result is an odd power if we started with an even root. And then finally down here at the bottom, if we have the cube root of x to the 12th, this should be x to the 12 over 3, which will turn out to be x to the 4th. And we don't have to worry about absolute value bars anytime it's odd, just the even ones. Now we've got an application problem. You'll see one of these in your homework where we've got the distance to the horizon from an observer's point of view over the ocean. If the person's eyes are 5 feet above the ground and standing at a 123-foot cliff. So distance to the horizon uses this formula right here, where distance is d and h is height. So we just need to know how high we are above the ground. Now the height is 123 plus the 5. So we put the height inside here as the square root of 2 times 123 plus my 5. And that's going to be 2 times 128. And so my distance is going to be 2 times the square root of 128, or the square root of 256. And the square root of 256. So the result is 16, and I believe miles is what the formula is given as. So I think this was miles that I didn't type in here. So 16 miles to the horizon based on the input of my 123 plus my eye height, which is 5 feet above the ground. All right.